Welcome to our next lecture in statistics at Dallas College with Professor Bailey. We are beginning chapter 4, where we're going to start looking at probability and basic probability. In this first place, we're going to learn about vocabulary such as sample spaces and how to do analysis with these. We're going to learn how to compute and interpret probabilities and approximate probabilities using the empirical method. Probability experiment is one in which we do not know what any individual outcome will be, but we do know how a long series of repetitions will come out. For example, when we flip a coin, we don't know if the coin's going to come out heads or tails, assuming it's a fair coin. But we do know if it is a fair coin means just that it's not fixed, like it's a double-headed coin would be an unfair coin. This is just a normal coin with a head side and a tail side, hence the name fair. And we don't know what's going to come out, but we know if we keep doing this experiment like 1,000 times, that we should get about half times heads and half times tails. Not exactly, but somewhere in there. And the longer we go, the more closer it should get to 50-50. The probability of an event is the proportion of times that the event occurs in the long run. The probability of an event is the proportion of times that the event occurs in the long run. So our experiment is flipping the coin. Okay, the event might be we flip, when we flip, we get a heads. The event is getting a heads when we flip a coin. And so the probability is about 50%. We know that because there's two sides, right? It's equally likely to have either one. So the probability of this event, if we do it a large number of times, a long run, will come out to about 50%. And I think I hit that already. There's something called the law of large numbers, that as we do the same experiment a large number of times, and if we keep repeating that experiment, the proportion of times that a given event occurs will start to approach its actual probability. So you can see here, this graph on the right is tossing a coin, the number of tosses, and the measure on the left is the proportion of heads that we got. So when we tossed it the first time, we got a head. So we got a proportion of 1 out of 1. When we tossed it a second time, we got a tails, and so now our proportion is 1/2. 1 was heads, 1 was tails, so we had 1 out of 2 was heads. When we tossed it the third time, we got another tails, so now we had 1 out of 3, or 0.3 was our 0.33 was our proportion. Okay, and then as you can see, we go across here doing the same experiment, flipping the coin 5 times, 10 times, 100 times, 1,000 times, and 10,000 times. And you can see, and this is very normal, that you're going to have wild variations in the first few series, but then overall it's going to average out until we get to closer to our probability. And that's all the law of large numbers is saying, is the more times you do the experiment, your event should be approaching its probability. Now there's another law called the law of averages, and this is not a real law. It does not work mathematically like laws. This is more an intuitive law where we think something's going to happen. It's really quite simple. So the law of averages says if you have a repeated pattern that is higher than probability, then the next experiment has a higher likelihood of a different value. Now what is this saying? So let's say we do this flipping coin experiment again, and we get 10 heads in a row. The law of averages says, oh, it's much more likely that the next flip will be tails. Well, it's not more likely. The coin hasn't changed. You have a 50-50 shot of getting heads or tails. And so this is kind of like an intuitive, your brain misleading you. Um, this is not a real law. This is false. The repeated pattern does not change the probability of the next flip or whatever experiment we're doing here. And this is what's called the gambler's lie. So, you're stuck there, you're betting on tails, and it keeps coming up heads. You stick there because it's got to be tails soon, it's got to be tails soon. And so this is the law of averages, and it is not true, it is false. You have no idea what's coming next in a fair experiment. Okay? Just because you had 5 or 10 heads in a row doesn't mean you're going to get tails next. Okay? The list of all possible outcomes of a probability experiment is called a sample space. So here I want you to try to figure out what the sample space is. For example, again, it's just a list of what's possible. If we toss a coin, what's possible for each toss? Hit pause and try to answer these 3 questions. Okay, I'm going to continue on. If we toss a coin, we have 2 possibilities. We either flip a head or we flip a tail, right? And so you can see here it's just a list. This is in set notation, heads or tails. This is our sample space. This is normally how we notate it with these special kind of brackets. When we roll a die is the singular of dice. What are the possibilities? Well, most die are 6-sided die. That's what we're talking about when we don't explicitly say it. So we have the possibility of 1, 2, 3, 4, 5, 6. Okay. The selection of a student at random from a list of 10,000 at a large university. So we have a list of 10,000 different names of students at a specific university. So that list, or that 10,000 names, is our actual sample space. There are 10,000 possible outcomes when we select a student at a random from a list of 10,000. We're often concerned with occurrences that consist of several outcomes. For example, when rolling a die, we might be interested not in a specific number, but in rolling an odd number. Okay? So notice if that is our event, we want to see if we can roll an odd number. This corresponds to the answers 1, 3, or 5 on the die, those sides, from the sample space of 1, 2, 3, 4, 5, 6. In general, a collection of outcomes of a sample space is called an event. Once we have the sample space, we need to specify a probability of each event. This is done with a probability model. We use the letter P to denote probabilities. For example, the probability that a tossed coin lands heads is P of heads. If A denotes an event, the probability of NA is P of A. And so when we're trying to figure out the probability, what we look at is the number of outcomes in the event. Up here where we were rolling an odd number in a die, we had 3 outcome possibilities, 1, 3, 5. That's our numerator. Divided by the number of outcomes in the sample space. How many possible outcomes were there? 6. So for our event of rolling an odd number on a die, we would have 3 divided by 6, or 1/2. Okay. So you try it now. As long as the sample space that all the outcomes are equally likely, then we can use this formula. Okay. So try this example. In the Georgia Cash for Lottery, a winning number between 0000 and 9999 is chosen at random, with all the possible numbers being equally likely. What is the probability that all 4 digits are the same, like they are here, 0s or 9s? Okay. So see if you can do this. Hit pause and try it. and then come back. So the two things we want to do is figure out the total number of outcomes and the number of outcomes in our event, okay? So how many ticket numbers are between 0000 and 9999? Well, there's 9,999 plus this additional one. So we have 10,000 possible outcomes. How many event outcomes? Well, notice here we have 0000. The outcome is that all the digits are the same, so we have 1111, 2222, 3333, 444, and that gives us 10 possible outcomes. So when we plug these values into our probability model, we get 10 out of 10,000, or 0.001 is our probability that all four digits will be the same. 1 in 1,000 or 10 out of 10,000. The probability of an event is always between the numbers of 0 and 1. Okay? So any event A will have a probability between 0 and 1 inclusive. If event A cannot occur, then we say that this is an impossible event and its probability equals 0. If you have 0 probability, it will never occur and it's an impossible event. For example, maybe we are rolling a die and we say that our event is rolling a 7. Well, 7 isn't on the die, so you will never be able to roll a 7, so the probability of rolling a 7 is 0. If A is certain to occur, then the probability equals 1, and we call this a certain event. So if you're going to get that response every time, or you're going to always make sure that happens, then it's an absolutely certain event. For example, instead of saying getting a 7 when we roll a die, we say we're going to roll a die and get a number less than 7. Well, all the numbers on the die are less than 7, so the probability of this event is equal to 1, 6 out of 6. There are 6 outcomes in the sample space, and there are 6 outcomes that are less than 7, so it's 6 out of 6. Now let's get it a little more difficult, okay? A penny, a nickel, and a dime are tossed, denoting a head by H and a tail by T. We can denote these 3 tosses in order: penny, nickel, dime. For example, HTH means we got a heads for the penny, a tails for the nickel, and a heads for the dime. Okay? Assume these outcomes are equally likely. What is the probability that all 3 tosses are the same? HHH, all heads or all tails. So we already have the numerator, right? What are the how many possible outcomes? There's only 2, that they're all the same. They're either all heads or they're all tails. So we know the numerator. But what is the denominator? Some people think it's just 3 because you're tossing 3 different coins. But remember, you have 2 options on each coin. So then sometimes people think it's 6, 3 times 2. The way to do this is really a way to visualize this is something called a tree diagram. So when we first toss the penny, we can get a heads or a tails. And next we toss the nickel. Well, the tree continues to grow. If we flipped a head, then the nickel possibility is heads or tails, those 2 branches off of the penny heads, but also there's 2 branches off the penny if we drew, if we flipped a tail. Here it's a little bit easier, okay? So this is our penny, right? We flip the penny, we get a heads. We flip the penny, we get a tails. These are the 2 possibilities. Now we flip the nickel. We can get a heads, so we have heads, heads, or we can get a tails, heads, tails. But we get those same 2 possible choices if we first flipped a penny tails. Again, the nickel is heads or tails, So notice automatically now we have more options. We have heads, 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 tails, tails, heads, tails, tails. Often people will say, well, wait, these are the same thing, heads, tails, tails, heads. No, they're not, because they're different coins. And so there are really two ways to get tails, heads on these two coins, right? Even if these were flipping 3 pennies, this would still be a different option between the first flip and the second flip. This could be just flipping one coin 3 times and you'd have the same outcomes. And then the last is the dime, excuse me. So again, we have heads, tails off of each of the options after the heads, 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 tails, tails, heads, tails, tails. And so now you can see we have 1, 2, 3, 4, 5, 6, 7, 8 options, not 3 times 2, but with our with our tree diagram, we can see there are 8 possible outcomes for this. Tree diagrams are a very simple way to kind of look at experiments that have repeated actions, like flipping a coin 3 times, or in this case, flipping one coin and looking at the series of outcomes. So our possible outcomes are 2, all heads or all tails, out of total of 8. So we have a 1 in 4 chance of getting all heads or all tails. Our probability is 1/4. Let's look at a little bit more complicated exercise. Here, we're rolling 2 die. Each is a fair, which means that each result is equally likely. This is very similar to our last experiment where we flipped 3 coins. But now each die has 6 possible options. So when you roll the first die and you get a 1, there are actually 6 possibilities for the second die, right? 1, 2, 3, 4, 5, 6. So you could have a 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Okay, so see if you can figure out what is the probability that the sum of the dice equals 5. All right, so hit pause and try this, and then hit play when you think you've figured it out. The hint that I have is to construct a sample space. You can do this with a tree diagram. And note that there are more than 12 outcomes. It's not just 6 for each die times 2. How many, and then you also have to figure out how many event outcomes, how many rolls of the die add up to 5 of the 2 die, okay? So the first thing we could do is we could build something that looks like this tree diagram. This is the one we did before, but instead of when we flip a coin, we have 2 options. When we flip a coin the first time, we have 6 options. 1, 2, 3, 4, 5, 6. And then off of each option, we have 6 more. Okay, so this is for flipping a coin, but we would see that we'd have 6 branches to 1, to 2, to 3, to 4, etc., all the way to 6. But off branch 1, when we roll the second die, we would also have, so we'd have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Okay, and so for a die, it would look something like this. The first roll is either a 1, 2, 3, 4, 5, 6. And the second roll is 1, 2, 3, 4, 5, 6. So you'd have all of these options. So you have 6 times 6, which would give us 36 possible options. Then we'd have to look through here and figure out which of those, how many of those equal 5. Well, 1 plus 4 equals 5, 2 plus 3 equals 5, 3 plus 2 equals 5, and 4 plus 1 equals 5. We can't do 5 because we don't have a 0. We can't do 6. So we had 4 options that equal 5. When we're doing die, another way to look at it is almost as if it was a multiplication table where we list both the first and the second roll. To me, this is a little bit easier to see, but the tree diagram works just as well. And then here we can look at the pairs. This is the first die, this is the second, so we get 1, 1, then 1, 2, etc. And again, sometimes folks will say, well, wait, isn't 1, 2 really the same thing as 2, 1? You don't really know which die is which die. No, it's not, because you do have 2 separate rolls that are equal, so it increases the probability of that. Okay, so then we're just going to go through and look for the ones again that add up to 5. And again, one of the things that's normally when you're looking at sums or something, they usually happen in diagonals. So again, we have 4 possible outcomes that of our event out of 36 total, or 1 out of 9. Sampling an individual from a population is a probability experiment. The population is the sample space. Everyone in the population represents a possible outcome, and members of the population are equally likely outcomes. Again, we do random selection so that every member has an equally likely potential of being selected. All right. So let's try another experiment here. There are 10,000 families in a certain town, and they all responded as follows to a survey: own a house, own a condo, rent a house, rent an apartment. And you can see the number of respondents, and if you add all these up, you'll get 10,000. This is a pretty simple experiment or exercise, so go ahead and hit pause and see if you can answer these 2 questions. Okay, so we continue on. A pollster samples a single family from this population. What is the probability that the sample family owns a house? So again, the sample space is 10,000, the number of people that are possible, the number of families that are possible to answer, and we're looking for the probability that someone owns a house. Well, how many people own a house? That's the number of the event. How many people or how many possible outcomes for owning a house? That's our numerator. So we get 4753 over 10,000, which is 0.4753. Okay. What is the probability that the sampled family rents? Now we have 2 probabilities. We have rent a house or rent an apartment. So we're going to add these 2 together because both of these are renting. Okay. Notice in the first one, it says the family owns a house. Just this one. If it just said owned their home, then we would have added these 2, which is what we're going to do for the second one. So the numerator is 912 plus 2857, and the denominator is still 10,000. Okay, and we get 0.3769. All right, so this is pretty straightforward, pretty simple formula. The number of outcomes in the event divided by the number of outcomes in the sample space. An unusual event is one that is not likely to happen. In other words, the event whose probability is very small. There's no real hard and fast rules as to just how small a probability needs to be before an event is unusual. But we're going to use kind of an agreement. A rule of thumb is when we just make an agreement that we're all going to do the same thing. And so for any event whose probability is less than 0.05, that's 5%, 5 out of 100, we're going to consider that to be unusual. So try this one. In a college of 500 students, 150 are math majors. A student is selected at random and turns out to be a math major. Is this unusual? Again, hit pause and try this. What we're trying to do is calculate the probability and just compare it to 0.05. If it's below this, then this is an unusual probability, an unusual event. If it's equal to or greater than, we're okay, then it's just a normal event. So when we calculate 150 math majors, the number in the possible in the event, divided by 5,000, the sample space, we get 0.03. 0.03 is below 0.05, so we event. Remember, the law of large numbers says that if we repeat a probability experiment a large number of times, then the proportion of times that a particular outcome occurs is likely to get closer and closer to its actual or true probability. The empirical method relies on the law of large numbers. That is, it repeats the experiments many times and figures out where all the people fall out in the diagram. It uses the outcome proportion to approximate the probability. So let's look at this. In a recent year, there were 752 births in the U.S. to low birth rate babies, less than 2,500 grams, while 3,477,960 babies 960 were the babies with weight greater than this. Approximate the probability that a new baby is born low birth rate. Okay? Be careful here. A lot of times students will, again, hit pause, try this, and then I'll tell you the careful. So be careful here because a lot of times students will just see two numbers and just automatically multiply them. We know that we're looking for low birth weight, which is the first number, 313,000. But there were 3.4 million babies with weight greater than that. But that's not the population. The population is the total of both of these, low birth and not low birth. So be careful with these. Okay. So the approximate probability of low birth rate is 0.08, so about 8% of the time. All right. So again, this is the list of objectives you should know. You might hit pause for a minute, make sure that you feel comfortable with these, and that you have notes in your notebook. Next, we're going to look at some more complicated events in 4.2. A compound event is an event that is formed by combining two or more events. Okay. One type of compound event is of the form A or B. A or B. This event is true if the event A occurs, or the event B occurs, or A and B occurs. Okay? The event A or B occurs whenever A occurs, B occurs, or they both occur. A, B, or both. A or B or both. Probabilities of events in this form, A or B, are computed using this general addition rule. So we calculate the probability of A, we calculate the probability of B, and then we subtract any probability of A and B. Now remember, and is an intersection, and what this does is it avoids us double counting. Okay? It avoids us double counting. If A and B do not have any members in common, then this would be 0, that there's nothing in A that's also in B, and then we would just add the probabilities. All right. See if you can do this probability. You've got the formula at the bottom. 1,000 adults were asked whether they favored a law that would provide support for higher education. In addition, each person was classified as likely to vote or not likely to vote based on whether they voted in the last election. What is the probability that a randomly selected adult is likely to vote or favors the law? So we're looking for likely to vote or favors the law. Again, see if you can do this. So we're going to look for the probability of likely to vote, probability of favors the law, and we're going to subtract the probability of likely to vote and favors the law, which is easy to see here. So we have likely to vote. It's all three of these sum. The probability likely to vote is all three of these. Likely to vote is these three columns. It's the entire row 1. We know the denominator is 1,000 because that's how many total. So we're going to add these three, divide by 1,000. The probability of favors the law is these two, right? Is this column. Column 1, row 1, and row 2. It's the sum of these. All right, so 372 and 151. So there's the formula. Here's the number likely. So the probability likely to vote. This is what I just did. Now we're going to do favors. The number of favors, 372 and 151. So the probability of favors is that total over 1,000. And now we need to do, that's both, probably and in B. How many people are likely to vote and favor the law? Likely to vote and favor. It's just 372. So we have 372 over 1,000. And notice this, we are subtracting out. Okay. So we figured out the first for the three parts: the probability likely to vote, probability favor the law, probability likely to vote and favors the law. We just plug them into the formula: probability A, probability B minus probability A and B. So we get a probability of 87%. And there I just showed it. You could do it but with just the numbers too. Okay. Here we have another possibility. This is just to get some more practice. We can see that we have some non-college graduate folks in each job and some college graduate folks, and it's asking you to do these three types of problems. So hit pause and try these and see if you can figure them out. So what's the probability that a randomly selected worker is a college graduate? This is the number in college over the total. Okay. This does not tell us how many is total, so we're going to have to add all these up. Non-college graduates get a total, add all the college graduates get a total, and then we add those together to get the sample space and divide by the total of college graduates. I'm just giving you the answer here. You should be able to figure this out. What is the probability that the occupation of a randomly selected worker is sales and office or is production and transport? So we're looking for the probability. It doesn't say anything about college, so we're not going to worry. So we're going to add these two numbers up. This is the probability sales and office. This is the probability of production and transport, the last row. Notice there is no indication that people can select multiple. So there's no overlap. There is no sales and office and production and transportation. So all we have to do is find the probability of sales and office, 22,000 plus 7,000 over the total, plus the probability of 14,500 plus 1,308 over the total will give us that property. Okay. I've got the actual answers here, so you can actually try these problems. It's a really good idea before you get into the homework. All right. And finally, what is the probability that a random selected worker is either a college graduate or has a service occupation? Okay. So now we're looking for the probability that a college graduate or service, college graduate or service. So we've already done the college graduate, the total of this over the total of college graduate column over the total of all of these. That's the probability of the college graduate, which we saw in the first one. The probability of a service occupation would be to add row 2, divide by the total. And then, of course, we have to subtract out the probability of a college graduate service occupation. So we'd have to subtract out 2,385 divided by the total to get this final answer. That's from the last problem because there was no overlap, and then here's what we see. All right, so you can try these problems and get a little more practice with the calculation. So this is just what I said before. If two events are mutually exclusive, this means there's no overlap. There's no answers in event A and B. There's no intersection. There's no members in both. So here's an example. Event A is the die comes up 3. Event B is the die comes up an even number. 3 is not an even number, so there is no number. There is no outcome that's in both. A fair die is tossed twice. Event A is one of the tosses is heads. Event B is one of the tosses is tails. Okay. You cannot have a toss that is heads and tails. So this is also I'm sorry, because it's 2 die. My bad. This is not mutually exclusive because we're tossing it twice. It is possible to toss it once and get a head and get another toss and get a tails, because remember when we do that tree diagram, we're going to have heads, tails, heads, heads, tails, heads, tails, tails. So there's 2 rolls that are actually in common. My bad on the way of explaining that. Okay. Suppose that a college student is chosen at random. Determine whether events A and B are mutually exclusive. The student is older than 21. The student is taking a statistics course. Can someone older than 21 take a statistics course? Of course they can. Of course they can. So this is not mutually exclusive. This is not mutually exclusive. The student is an only child. The student has a brother. If you are an only child, by definition, you do not have any siblings. So this is indeed mutually exclusive. All right. So if events A and B are mutually exclusive, then there is no intersection, as we just saw, like with the child, only child versus a child with a sibling. So this goes to 0. So the formula just simply is adding the two probabilities. If you're looking for probably A or B and they have nothing in common, then you just simply add the probabilities. And be careful, like I said before, when I was looking at that one where you flipped a coin twice, and one event was flipping it heads and one was flipping it tails. Because you're flipping it twice, it is possible to have intersection there. All right. Let's try another one. In a recent year of the Olympic Games, a total of 11,544 athletes participated. Of these, 554 represented the United States, 314 Canada, 125 Mexico. What is the probability that an Olympic athlete chosen at random represents the US or Canada? So we could do this, but we notice here, can someone represent Canada and the US at the same Olympics? No. So this last piece, the probability of A and B, is 0. So all we have to do is to find the probability that we select a US athlete plus the probability that we select a Canadian athlete. So we know we have the total up here and we have the individual. So we have the probability of US, which is 554 over 544, and the probability Canada is 314 over 544. We do the math and we get 0.075. So roughly about 7.5% of the time we could pick this as a probability. In a statistics class of 45 students, 11 got a final grade of A, 22 got a B, and 8 got a C. What is the probability that a randomly chosen student got an A or a B? Again, you can't get an A and a B, so it's just the probability of A, 11 out of 45, and B, 22 out of 45. What is the probability that a randomly chosen student got an A, B, or C? And here we got 11 out of 45, 22 out of 45, and 8 out of 45. They don't mention any other grades, but I noticed that those three numbers do not add up to 45. If these were all the grades, then we would expect the probability to be a 1, but it looks like some students also failed. So we again have 11 out of 45 plus 22 out of 45 plus 8 out of 45 for the C, which gives us 31 out of 45 or 91% probability. Okay. Complements are the outcomes that are not the event. The language can be a little bit confusing mathematically, okay? Because we think of maybe sometimes at least means less than, but it doesn't, okay? All right. So let's look at this example. 200 students were enrolled in a statistics class. Write events that are complements of the following events. If exactly 50 of them are sophomores, how many are not sophomores? So here we would say that 150 of the students are not sophomores. Notice how that's the complement of the event. The event is sophomores, so we're looking at not sophomores. So see if you can do the other two. If more than 50 of them are sophomores, then how many are not sophomores? less than 150 are not sophomores, because more than 50 are sophomores. That means that less than what's left, 150, are not sophomore. Less than 150. Okay? If at least 50 of them are sophomores, this one's where it gets a little confusing. So this means 50 or more are sophomores. So then 150 or less are not sophomores. Again, be careful of these at least and at most, because the language, if we go too fast, we realize, if we think about it, we know at least means 50 or more. At most means 50 or less. Okay? And just sometimes less than and least, we think of those, your brain kind of organizes those together. So the rule of complement says that the probability of a complement equals 1 minus the probability of A. Okay, so let's look at an example. According to the Wall Street Journal, 40% of cars sold in a recent year were small cars. What is the probability that a random chosen car sold in that year is not a small car? The probability not a small car is 1 minus the probability of a small car. So 1 minus 0.4 would give us 0.6. So the probability that a randomly chosen car sold in that year is not a small car is 0.60, or roughly 60% of the cars were sold. Okay. This brings us to the end of probability in chapter 4.1 and 4.2. Make sure you review this list to make sure you feel comfortable. If not, go back